Hi guys, this is AS Chemistry, Organic Chemistry, and we are looking at halogenoalkanes. Question 5. Another hydrocarbon W with the formula C4H8 reacts with hydrogen bromide to give two products X and Y. X and Y are structural isomers of molecular formula C4H9Br. Reaction of X with aqueous alkali produces an alcohol Z that has no reaction with acidified dichromate 6. Give the structures and names of the compounds W, X, Y, and Z. So in order to give the structure and name of this compound, we can start off with the alcohol Z because it does not undergo an oxidation reaction, which means that it is a tertiary alcohol. And because it is a tertiary alcohol, so it would have a carbon atom with an OH group attached to it, to which there would be three different R groups present. And since the molecular formula contains only four carbon atoms, each of these R groups would be a CH3 group. And since this alcohol is made from the bromoalkane X, so bromoalkane X would be a similar structure with the OH group being replaced by the Br atom. So it would be a tertiary halide. So this is the structure of X. And now we need to understand how to make W and Y. So making of W is easier because we know that the OH is attached to a carbon atom to which there are two CH3 groups present, because the third CH3 group would be produced when a hydrogen adds on to the CH2 group in an alkene, converting it into a CH3 group. So we would have two carbon atoms with a double bond between them, one of them having two CH3 groups attached on it, and the other one having two hydrogen atoms attached on it. When HBr would be added, Br would be added on the carbon atom on the left, and uh, H would be added on the carbon atom on the right to give rise to X. And if Br is added to the carbon on the right and hydrogen to the carbon on the left, then we would have formation of compound Y, which would be CH2Br on the right. Then we would have CH attached to two CH3 groups. And now to name all these four compounds, we would start off with naming of W. So W would be 1, 2, and 3. It's propanene, and there is a substituted methyl group on the second carbon atom. So the name of W would be 2 methyl prop 1 ene. For X, the name would be 2 bromo 2 methyl propane. For Y, the name would be 1 bromo 2 methyl propane. And for Z, the name would be 2 methyl propane 2 all. So in this way, we have identified all the four structures W, X, Y, and Z along with their IUPAC names. When W reacts with hydrogen bromide, more X than Y is produced. Explain why. So X contains a tertiary carbocation which has a greater positive inductive effect present due to the presence of 3 electron donating R groups. Y is a primary carbocation containing compound. The tertiary carbocation is more stable, so its formation is preferred. So whenever alkene W will have HBr added onto it, more of X than Y would be formed because air is a more because X is a more stable compound than Y. So a more stable compound would be preferred when a reaction takes place and a product is formed. There would be some of Y forming, so Y would be called the minor product, whereas the major bromoalkane that would form would be X, so it would be called the major product. Question 6. Give the structures of the four structural isomers of C4H9Br and identify each as primary, secondary, or tertiary. So we can start off with the tertiary halide in which we have four carbon atoms in a straight chain. So CH3, CH2, 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 and then Br. And we can continue with the structure similar to this, but substituting one of the carbon atoms in the chain as a substitute group. So we can have CH3 attached to CH, to which we attach a substituted group CH3. Then we have a CH2 remaining, and then we have a Br. So both of these isomers are examples of primary halides. And now we will make a secondary and a tertiary halide. In a secondary halide, we would need a carbon atom with one hydrogen atom attached to it and a bromine atom, and on the remaining two positions we should have R groups present. So there are three carbon atoms remaining. So on one side we add a CH3 group, and on the other side we add a CH2 and a CH3 group. And as for the tertiary halide, the carbon atom to which the Br atom is attached to should be attached by three R groups, making it a tertiary halide. So these three R groups would be CH3 because the molecular formula only contains four carbon atoms in total. So these are the two primary, a secondary and a tertiary halide that can form, that has the molecular formula C4H9Br. And just to name these compounds, the first one would be called 1-bromobutane. The second one would be called 2-methyl. So it starts off with 1-bromo. 1-bromo, 2-methyl propane. The third compound would be called 2-bromobutane. And the fourth compound would be called 2-bromo, 2-methyl propane. Name the isomer of C4H9Br that contains a chiral center and draw the three-dimensional structures of the two optical isomers. So the one that has a chiral center is called 2-bromobutane, because we can see that 2-bromobutane has a carbon atom that has a hydrogen atom attached to it along with a bromine atom. Then we have a CH3 group attached to the right side of that carbon atom and a CH2 group attached to another CH3 group on the left side of the same carbon atom. So in this way, the two optical isomers would have a hydrogen at one end, a bromine at the other. On the right side of the isomer on the left, we would have a CH3 group and a CH2 CH3 group on its left. And in the isomer on the right, we would have a CH3 group on the left and a CH2 CH3 group on the right. And these are the two optical isomers of 2-bromobutane. Give the full name of the mechanism for the reaction between aqueous sodium hydroxide and bromoethane. Since bromoethane is a primary halogenoalkane, it will undergo the SN2 reaction mechanism, which is known as nucleophilic substitution. Complete the diagram below to represent this mechanism. Include all necessary curly arrows, partial charges, and lone pairs. So we would have a partial negative and a partial positive charge present on the carbon and the bromine atoms. We would have a lone pair of electron present on the oxygen atom of the OH group, which would be attracted towards the positively charged carbon atom, which would result in the C-Br bond breaking. And once we have the oxygen forming a bond with carbon, the bond between carbon and bromine would be completely broken, resulting in the formation of an alcohol from bromoethane, and the alcohol would be ethanol. And this is the requirement for the SN2 nucleophilic substitution reaction for bromoethane to be converted into ethanol. In the past, CFCs such as CF3Cl were widely used as refrigerants. State a property of CFCs which makes them suitable for use as refrigerants. The most important properties of CFCs to be used as refrigerants are they are inert and they are volatile. Because of these properties, CFCs have been used as refrigerants. State the damaging effect of CFCs in the upper atmosphere. They cause ozone layer depletion. Explain your answer. The CCl bond undergoes homolytic fission in the presence of UV light, forming chloride free radicals. These attack the ozone molecules and convert them into oxygen. And in doing so, the ozone layer gets depleted. So this is why CFCs are harmful for the environment. Question 7. Some reactions involving ethanol are shown. So ethanol in reaction 2 produces chloroethane. In reaction 1, chloroethane produces ethanol. and ethanol in the presence of acidified Cr2O72 negative ion, and with distillation produces Y. So if it is distilled, that means we are producing the aldehyde. So Y should be CH3CHO. And if we heat CH3CH2Cl with NaOH and ethanol, then X should be the alkene ethene. So this would be CH2 double bonded to CH2. So these are the two products X and Y that form in the reaction schemes shown. Identify the organic product X. So it is C2H4, or we can write CH2 double bonded to CH2, or we can mention the name ethene. So either of the three ways would be mentioning the organic product X. Nitric acid is added to the products of reaction of CH3CH2Cl with NaOH in ethanol. Silver nitrate solution is then added to the mixture. State what you would observe. So when NaOH is added, it would result in the formation of the alkene and NaCl. And upon addition of nitric acid, the remaining NaOH would be neutralized. And on addition of silver nitrate, the NaCl would react with silver nitrate, producing a white precipitate of AgCl. Write an ionic equation including state symbols for the reaction responsible for the observation in 2. So the ionic equation would be Ag positive aqueous ions from silver nitrate, Cl negative aqueous ions from NaCl, forming AgCl solid, which is the white precipitate that would be observed. Question 8. Halogenoalkanes are useful intermediates in the synthesis of a wide variety of compounds. 2-bromobutane reacts in two different ways with sodium hydroxide depending on the conditions. When warmed with aqueous sodium hydroxide, 2-bromobutane produces an alcohol that exists as a pair of optical isomers. Give the name of the mechanism of reaction between 2-bromobutane and aqueous sodium hydroxide. So if Br is replaced by OH, that means this is an example of a nucleophilic substitution reaction mechanism. Explain why the alcohol produced exists as a pair of optical isomers. The alcohol contains a chiral center in which a carbon atom forms four single bonds with four different atoms or group of atoms. So in this way, if a chiral center is present, then that particular compound will have optical isomers. Draw the three-dimensional structure of the two optical isomers of the alcohol produced in 2. So 2-bromobutane, when it will react with NaOH, will result in the formation of butane 2-ol. And butane 2-ol will be a secondary alcohol in which the OH group will be present on a carbon atom, to which there would be two different R groups attached. And since it is 2-bromobutane, the R groups will have to be CH3 and then CH2, CH3. So if we have hydrogen present on one side of the isomers and OH present on the other side, the remaining two positions would be occupied by the R group. So one of the positions would be occupied by a CH3 group and the other position would be occupied by a CH2 and CH3 group, resulting in the formation of the two optical isomers of butane 2-ol. Heating 2-bromobutane with ethanolic sodium hydroxide produces a mixture of three alkenes, two of which are a pair of geometrical isomers. Give the name of the mechanism of the reaction between 2-bromobutane and ethanolic sodium hydroxide. So this is an example of an elimination reaction mechanism, and the type of reaction that occurs here is called dehydrohalogenation, in which a hydrogen and a halogen atom is removed from a bromoalkane and it results in the formation of alkenes. Draw and name the structures of the pair of geometrical isomers formed by reaction of 2-bromobutane with ethanolic sodium hydroxide. Since the bromo atom is on the second carbon atom, it would mean that the double bond would be present between the second and the third carbon atom, which would mean that both of them will have a CH3 group attached to them and a hydrogen atom attached to them as well. So this particular alkene will be known as cis butene because the CH3 groups and the hydrogen atoms are present on the same side of the double bond, and in its isomer the CH3 groups as well as the hydrogen atoms would be present facing in the opposite directions to each other on the two carbon atoms. It will still remain butene, but instead of cis butene it will be called trans butene. Name the third alkene produced by reaction of 2-bromobutane with ethanolic sodium hydroxide and explain why it does not show geometrical isomerism. So the third alkene would be but1ene, and the structure of but1ene would be C double bonded to C. Then we would have one carbon atom with two hydrogen attached to it and another carbon atom with a hydrogen and a CH2 and a CH3 group attached to it. So the explanation here would be, since a carbon atom has two hydrogen atoms present on it, which are the same groups, it will not show cis trans isomerism, because the requirement of cis trans or geometric isomerism is that two groups on both the carbon atoms having a double bond between them should be the same, not two groups on the same carbon atom. Since the carbon atom in but1ene on the left has two hydrogen atoms attached to it, it does not meet the requirement for cis trans isomerism. But2ene does meet the requirement of cis trans isomerism because both the carbon atoms with a double bond between them have hydrogen on both carbon atoms and as well CH3 group on both the carbon atoms. So with respect to the CH3 group or with respect to the hydrogen atom present, but2ene does show cis trans isomerism. But1ene does not because the carbon atom on the left has two hydrogen atoms present, which does not meet the requirement of this type of isomerism.